Hello, I'm Eleanor Frajka-Williams, a professor at the University of Hamburg, and unfortunately, due to flight issues, I was unable to make it for the meeting in Rhode Island in person, which is a real shame since this workshop seems like a superb opportunity to get oceanographers and geophysicists together and talking about, well, in my case, ocean bottom pressure. In any case, thank you to the organizers for bringing us together, and I'm looking forward to discussions. This talk is pre-recorded, but I am hopefully available to take real-time questions or discussion points afterwards. So I'm going to speak today about drift-free bottom pressure in order to reconcile methods for measuring ocean circulation. So I am, of course, a physical oceanographer. And so I'd like to give a little bit of background to the problem that I'm going to talk about today, which is how we measure ocean circulation or ocean transports using instruments that may be up to 6,000 kilometers apart. And the short answer is we do this through geostrophic balance. And the problem then is that in applying this in the ocean, we actually use a particular form of geostrophic balance, which requires us to supply an unknown constant of integration. And so this constant of integration becomes the problem. And this is where a potential solution to solve this problem, which I'll describe in a little bit more detail why it's really becoming a problem for measuring ocean transports, is that ocean bottom pressure can potentially help solve this issue. But in order for that to be the case, we need to know how good the drift-free, the error on the drift-corrected pressure measurements is at the end. And I'll also give a little bit of an overview of the fieldwork plans in our Horizon Europe project EPOC, which I realized, I just looked through some of my old emails. It's been a long time in the making. I think it was since August 2018 when Kate Reichert, Nick Harmon, and I first started talking about this. So sensors just got deployed in February 2023. So it's been a while. Okay, so a little bit of background. This is a schematic diagram of the Atlantic meridional overturning circulation, or the Great Ocean Conveyor. This view is, of course, looking northwards in the Atlantic, where we have northward flowing warm waters, including from the Gulf Stream, in the near surface in the top 1,000 meters in the subtropical North Atlantic, that then gets transformed at high latitudes and comes southward as dense, deep, cold water. And we're interested in this for a number of reasons, which I'm not going to go into today, but you could always check out the 2004 movie, The Day After Tomorrow, to learn a little bit about the overturning circulation. But what I do want to discuss today is how we measure, a little bit about how we measure these ocean currents. And we don't do it by making direct velocity measurements all across the Atlantic. So we have methods to measure velocities in the ocean using acoustic sensors, but we can't put that across a span of 6,000 kilometers and surface to 5,000 meters in order to measure velocity everywhere and then figure out in the net how much is going northward and how much is coming southward. So instead, we use geostrophic balance. And this balance, which I'll show on the next slide, allows us to use just a small number of moorings on the boundaries of the Atlantic. And so I'm guessing Chris Hughes has already spoken about this yesterday. And in the case of 26 North in the Atlantic, this is actually an out-of-date slide. We no longer have moorings at the Mid-Atlantic Ridge, but they're concentrated on the eastern and western boundaries of the Atlantic. And so just from a small number of moorings, we can then infer the north-south velocities across the entire section. So this is the equation that we start with, where we have velocities, north-south velocities on the left-hand side, which are then estimated from the horizontal or the zonal gradients in pressure. And you could apply this at every depth, and we're interested for the overturning circulation in the velocities across the entire basin span. And it means that you just need to know the pressure difference on the east and west the continental slopes. However, pressure mostly comes from the weight of the water above the sensor. And in order to estimate or in order to use those pressure measurements, you need to know exactly what depth that sensor was deployed at, which we don't usually know. But the pressure anomalies are what we're really interested in, and these arise from changes in the sea surface height, temperature and salinity, and seafloor depth, which is also typically ignored. And I'm guessing from her title that Kate Reichert is going to talk about this. And we additionally have the problem that pressure senses drift, which I'll talk about a little bit more, but I'm guessing other folks have already talked about this. And so the consequence is that we can't actually, because we don't know the positioning of pressure sensors, if we were to deploy them in the ocean, we can't actually apply this directly in order to estimate ocean transports. And so what we do at 26 North and at other latitudes in the Atlantic to measure the overturning circulation is we apply what's called thermal wind, which is just a different form of geostrophic balance, where instead of pressure on the right-hand side, instead of the zonal gradient of pressure, we have the zonal gradient of seawater density, which is a lot easier for us to measure. But the problem then is on the left-hand side, instead of velocity, we have the vertical shear of velocity. And in order to go back from the vertical shear to the absolute velocities, we need to integrate. And that's integrating relative to some known value at the bottom or at the surface, which is not actually known, which leaves us with the problem of an unknown constant of integration in order to actually estimate what our velocities are. Okay, so maybe it seems like not too big a problem. We can just sort of make some educated guesses. But the problem then becomes when this is applied at a whole lot of different latitudes in the Atlantic to estimate the overturning circulation in the subpolar North Atlantic, the OSNAP array, subtropical North Atlantic at 26 North and 16 North, and then the subtropical South Atlantic at Samba 34.5 South. Each of these arrays uses a different method to choose their reference velocity or to solve this unknown constant. So on the one hand, this seems like just a little methodological choice. On the other hand, it actually makes a significant difference or a substantial difference in the computed transports from the different arrays. And so just as an example, for 16 North and 26 North, these are the transport estimates of the overturning circulation of these two latitudes, 10 degrees apart. And over the overlapping time period, the time of writing of this paper, between 2004 and 2016, those overturning transports had opposing sign tendencies. And so these opposing sign tendencies were actually determined to be due to the methodological differences in applying the reference level transports. So it's a significant problem for understanding what the large scale ocean circulation is doing and where we have the potential to try and address this, maybe with drift-free bottom pressure sensors. So this is the solution, maybe. That instead of trying to guess or estimate what the unknown constant of integration is, that instead we measure those reference level velocities. And just to point out, it's a constant of integration for a vertical integral, but it can vary in time. And so we're really looking for the time varying reference level velocity. And we do have methods to estimate this from sea surface height or bottom pressure if we can estimate those well enough. But of course, sea surface height is very variable and still has residual error and spatial changes as well when you're trying to estimate between satellite data and where the actual positions of moorings are. And bottom pressure has, from our traditional sensor approaches, unconstrained drift of up to order 10 centimeters a year. And just to point out, 10 centimeters a year is an unacceptable level of error. 1 centimeter of error equates to roughly 1 sphere drip of error at 26 North. And if you just pop back to this slide here, 1 sphere drip of error, 1 sphere drip of drift over an annual time period, and you'd be wiping out your signal entirely. So just looking at the red curve here, went from positive 2 sphere drip anomaly to minus 2 sphere drip anomaly over 8 years. So about a half a sphere drip a year. Okay, so that puts some bounds on what we're trying to get out of our bottom pressure sensors. This is something I'm sure is familiar to all of you, that ocean pressure sensors experience exponential and linear drift. This is a classic paper by Randy Watts and Quintianus. And this is just a demonstration of what happens when we try and remove the drift and correct for it at 26 North. So these are traditional bottom pressure sensors, SBE 56, I believe, that have been deployed since 2004. And the top panel shows the pressure measurements after removing the first 50 days of each deployment. And so each of the colored lines is a different deployment, and the black line is an estimated average in some way over those records. I know. Actually, I don't remember what the black line is. It might be actually the Grace measurements of bottom pressure in liquid water equivalent. So that's why this is done in centimeters liquid water equivalent. And you can see, so for instance, in 2006, there was drift in the sensor from minus 10 centimeters to plus 10 centimeters over the deployment period, which becomes a bit of a problem. And then this is a correction method. After removing those first 50 days, you get rid of most of the exponential drift. You're left with linear drift, and you can stitch together the linear drift over time if you have these half overlapping records. So in the early days, each sensor was deployed for 2 years, 1 year overlapping, and now they're deployed for up to 4 years, 2 years overlapping. But in the end, you still can't reconcile the you have one more undetermined constant, which is this tendency, the linear tendency over the full deployment period, or the full record. So in this case, the 10-year record. Okay, so this is where our new drift correcting sensors come into play. So the two that I'm aware of are the RBR BPR0 and the Sonodyne Fetch A0A. And we are deploying these now as one part of the Explaining and Predicting the Ocean Conveyor project, the EPOC project. And just a little bit about it, it's funded through Horizon Europe. The duration is 60 months or 5 years from 1st July 2022. And it's trying to come up with a new idea, a new conceptual idea of what the overturning circulation is and to what extent it behaves like a conveyor belt and on what timescales. But one work package within this project is to design and deploy elements of a next generation observing system for the AMOC. And so one of the things that we particularly aimed to address is this problem that prevents us, this reference level problem that prevents us from really using observations from all the different arrays to gain a better understanding of the large scale overturning, the Atlantic-wide overturning circulation. So in this task, we are deploying drift-free bottom pressure sensors, and then the main work is to try and constrain the error in the pressure variability after recovery, which will be in a couple of years, and then at the end of this to determine whether the drift-free bottom pressure sensors do provide an opportunity to reconcile the large-scale ocean transport estimates from different arrays. And so we won't actually carry that out. We won't try and solve all of these problems at once, but it's really just to see if we can constrain the error on the measurement. And so the first two sensors were deployed at 26 North just at the end of February, thanks to Kate Reichert and Nick Harmon. So you can see these going in just east of the Bahamas, very nice weather there. And they'll be going in for, I forget if it's up to 4 or 5 years, but with the data downloaded in the intermediate time period so that we can try and carry out the work within the EPOC project during the duration of the EPOC project. So this just for the 2-year sort of proof of concept. And then also at 47 North, another Sonodyne Fetch and an RBR BPR0 to be deployed under tall moorings off of Flemish Cap. And so this is for another aspect of the EPOC project. And then we'll use it also to give us the dynamic height above the bottom pressure measurement. Okay, and just to give even a little bit broader picture of what's going on within the field of making ocean measurements. So these are, since this is a recognized problem of how we make ocean measurements, at OSNAP in the subpolar North Atlantic, Stuart Cunningham has deployed 2 of these A0A sensors since last summer. The ones that I just mentioned at 26 North went in from February 2023, and the ones at 47 North are going in from September 2023. And at 16 North, I think you'll hear from Uwe Send and Matthias Langhorst, also plans to put some in from possibly 2025, which I believe is their next deployment period. And so it's really a watch this space kind of a situation, because of course we're trying to first collect the data before we can analyze the data. And so at least for 26 North and 47 North, we expect that to come back in about 2 years, 1.5 to 2 years. And I just wanted to mention also that the smart cable project, so this has been, as I said at the beginning, a long time in the making. I think Kate, Nick, and I had between us 4 or 5 unsuccessful proposals to get this going. But another project that's been a long time in the making is the one that Bruce Howe has been spearheading to put in pressure sensors or smart cables, so telecommunications cables with sensors on them. And one of those sensors then is also expected to be bottom pressure. And this would offer an opportunity to make really long-term measurements at more or less fixed positions in the ocean. And if distributed along the continental slope, could really be applied to estimate ocean transports in a fixed infrastructure type of approach. So hopefully there'll also be discussions of that during this meeting. All right, thanks very much.